All right, so now we've determined if we have an A, we can figure out if it's diagonalizable. We can also figure out the diagonalization. Can we do the reverse? We definitely can. So let's look at this example. Let us suppose A is a 2 by 2 matrix with eigenvalue I'm going to call it lambda 1 equals 2. Corresponding to eigenvector v1, which is 1, negative 2. All right, so we have a 2 by 2 matrix A. We know an eigenvalue 2 corresponds with this eigenvector. And let's say we have another, so eigenvalue, I'm going to call it lambda 2 equals negative 3, corresponding to eigenvector v2, 1, negative 1. All right, so let's remember what this means, right? If we know that we have a matrix A and we know the eigenvalues and the eigenvectors that they correspond to, let's not forget what it means to be an eigenvector. Remember, this means that if we multiply A times our first eigenvector, we're going to get 2 times our first eigenvector, right? A times our eigenvector equals our eigenvalue times the eigenvector. Also, if you multiply A times 1, negative 1, you're going to get negative 3. 1, negative 1. All right, this is just by definition of eigenvector. So the question that I want us to answer, what is A? All right, you can do this a long way with algebraic manipulation, but we can also use the diagonalization theorem. So that is exactly what I'm going to use, that diagonalization theorem. So first, I want us to note that A is diagonalizable if V1, V2 is an eigenbasis for R2. All right, so remember, to be an eigenbasis or to be a basis, they need to be linearly independent. So 1, negative 2, 1, negative 1, these are definitely linearly independent vectors. So these two together will form a basis in R2 because there's 2 of them. All right, so I will say it is. Which is great for us because we can use the diagonalization theorem. So in order to figure out A, we can just use the fact that A is diagonalizable. Where P is just going to be the matrix you get by putting the eigenvectors together. And D is the matrix you get by putting the eigenvalues in the diagonal. All right, we can quickly and easily find P inverse. 1 over the determinant, that's negative 1, positive 2. All right, so we have our all the pieces to set up what A is. So now finding A is just multiplying these three matrices. So A is going to be our matrix P. Times our matrix D. Times P inverse. Right, and when we multiply this all together, we get negative 8, 10, negative 5, 7. This is our matrix A. And you can always check your answer by multiplying A times the eigenvectors. You should get the same things here. All right, so this is our section on diagonalization.